Hello viewers of YouTube, and in today's video we will see how to design a WhatsApp-like chat application during a system design interview. But before that, if you are new to our channel, we are software engineers from one of the FAANG companies, and via this channel we bring the best tips and tricks for you guys to crack your next tech company interview. With that, let's dive right in. So to approach any system design interview question, you have to understand that what things the interviewer is trying to test. The interviewer wants to know that how do you break down a giant system into subcomponents? How do you deal with ambiguity? They also want to know how aware you are about day-to-day technologies in the market like AWS or different types of databases. And at the end of the day, how clearly you can formulate and convey your ideas in a calm and calculated manner. This is definitely not a holistic list by any means, but something that is right on top of the list there. So in this video, we will start by gathering some of the requirements. This will help us drive the conversation with the interviewer and help us get a jump start during the interview. Next, we will dive into each specific component. We will use this opportunity to interact with our interviewer and showcase that how deep our knowledge base is and if we can take care of any ambiguity that is involved in the system design question. In the end, we will reserve some time to perfect our design and go over some of the potential bottlenecks and optimizations that we can apply. Before we proceed any further, we want to put a disclaimer here that this is only one of the possible approaches to solve this design problem. We researched thoroughly for it, but it might be a little different from what WhatsApp might have in place. So please do your own research as well to supplement the material, so you will feel more comfortable when dealing with this exact design question in a real live interview. So I think most of us already know that one of the core features of any chat application is to send and receive the messages. But this could differ if the user is online or offline, or if there are multiple users sending or receiving the messages like in a group chat. But underneath, all of these are just a variation of one-to-one messaging at the end of the day. So let's start by laying down some of these requirements in bullet points. First and foremost, our chat application should support one-to-one messaging between users, as we just discussed. Secondly, we see those single write, double write and blue write tick signs. So those are sent, delivered and read confirmation receipts. So we should also have them as well. Third, we should be able to share or send media, that is images or videos. We should also support some sort of push notification on mobile apps. And in the end, we can also design some additional features like last seen or used WhatsApp application or end-to-end encryption. So let's start by drawing the high-level design of WhatsApp application. We can think of WhatsApp as a client-server architecture, although we can also design it as a pure peer-to-peer architecture, aka P2P, to make it a truly distributed network, but that would be a discussion for another day. So here we will think of our users as clients, and then somewhere in a far away location, we have our data center hosting all those servers that interact with these chat applications and relays messages across between different users. So we will start off with our customers or users. We have Alice and Bob with us here, where Alice is sending the message to Bob. So once Alice types the message and presses that send button, the message will land onto the server. Here we have the chat service. Here the server reads the metadata from the message's body and figures out that message is meant for Bob. It then calls the backend service to check if Bob is online or not, and then the chat server to which Bob is connected to. So at this point, two things can happen. Either Bob is online. In that case, server will push down the message to the chat server to which Bob is connected to, which will eventually forward the message to Bob's phone. Or if Bob is offline, in that case, Alice's chat server would send this message to a transient server to store the message in the transient data storage. These transient messages will be forwarded to Bob once Bob comes back online. Fun fact for our viewers here, that unlike other chat applications like Facebook's Messenger or Skype, WhatsApp doesn't store your messages. That is, it temporarily stores the messages until it gets delivered. After that, there is no record of it at the WhatsApp end. So this looks like a sufficient enough high-level bird's eye view of the entire architecture for the solution. Now let's peel one more layer down on how this whole thing will play out in the real time with a super elaborative sequence diagrams for individual components. Yes, sequence diagrams are really great to visualize the state transitions of our system and brainstorm qualitatively that or if we are moving in the right direction or not. So here let's say that Alice is connected to chat server A and sends a message destined for Bob through this server. We can use a RESTful web service on these chat servers. So right now would be a very good time to write down the rough schema of the message being sent to the REST endpoint. We can start pretty basic here. We will have the first field as from user to tell the sender of the message, and the next field would be the to user. Obviously we need to know that where this message is destined to, and then the unique identifier for the request could be in the form of session ID that could be just generated on the runtime by any of the encryption library. And in the end we'll have like some sort of client metadata. We can also send some information like length of the message, version or mobile OS of the chat application that Alice is using. And finally, the most important thing, the message bytes itself. Once this blob of data hits the chat server A just unwraps the entire message and sends back a note or acknowledgement back to Alice that her message has been sent, or in other words is basically her message has been received by chat server A without any fault or any loss of that message during the communication. Now at this point chat server A needs to find out that which exact server Bob is interacting with. So that's when like chat server A calls this chat storage, which acts as a phone book to help other chat servers to find out the location of the users or which they are talking to in reality. Let's say Bob is interacting with chat server B, and so once server A receives this information from chat storage that Bob is communicating to chat server B, it forwards this message all the way to server B. Now it's server B's responsibility to forward that message to Bob successfully. Now at this point, if Bob is online and connected to server B pushes down this message to Bob's phone and sends an ACK back to Alice's phone that the message has been successfully delivered, and that's when Alice will see on her phone the two gray ticks for that message. That is a proxy that her message has made all the way to Bob's phone without any fault. And this doesn't really mean that Bob has already read the message, it just means that the message has been received by Bob's WhatsApp application. Now let's say after 15 minutes, Bob opens up his WhatsApp application on his phone and reads the message. Now his application sends a new message to Alice with an empty message body, but in the metadata saying that X particular message was read by Bob. And you can see the same flow happening from chat server B to chat storage server to find out chat server A for Alice's phone's current location or the communicating server, and then server B sends this message again to server A, and then server A forwards this message to Alice's phone, where Alice will see two blue ticks on the message that was earlier sent in the first step. Now this design works great if Alice and Bob both are online all the time and their respective talking servers are also working all the time. At this point, your interviewer can ask that what happens if Bob is offline or server B just can't particularly send that message to Bob at that point of time. One way that comes to my mind is to retry indefinitely, but it will just waste CPU cycles. So that is why we should implement something to transiently store these messages. The concept here is to store the undelivered messages in a separate data store if it is not delivered right away. Now at this point, we want to jump onto sending the media messages design part while also handling the communication for offline users. This will help us get the ball rolling in the limited amount of time that we have. So just like in previous scenario, Alice sends this image to chat server A, to which it is talking to in the first place. Then server A stores this message in a file server and returns the URL of that image back to Alice's phone, and also sends an acknowledgement to Alice's phone that her message has been sent to Bob, but in reality it is just being sent but not delivered. Now just like previously, server A queries the chat storage server to find out that which server Bob is talking to or connected to currently. But to its demise, server A finds out that Bob is offline. At which point, server A forwards this URL to a transient server, which makes a note of the URL in a transient storage for Bob. Now let's talk a little bit about how these messages are getting stored. So we can create a FIFO based queuing service that queues all these outstanding messages for each users in the system like this. Now let's say that Bob just came online. At this point, Bob will make a request for its outstanding messages and talks to server B. So server B queries this transient server to find out any outstanding messages for Bob, and at that point of time it just pops back the image URL that we just stored in our FIFO queues for Bob. Once this image is delivered to Bob's phone, all its references are deleted from the transient storage, the server B, transient server B, and the transient file server. Again, the same flow will happen to send the acknowledgement back to Alice's phone that the message is delivered, and there will be 2 gray ticks on that image. And again, that when Bob reads the message or like opens the image URL, it again sends the message back to Alice's phone about that Bob has just read the message and show 2 blue tick signs on Alice's phone for that particular image or media that was shared. So this is how we created a layer of transient persistence between Alice and Bob to temporarily store these messages whenever Bob is offline or any user is offline. Another fun fact for you guys, WhatsApp implemented a similar FIFO based queue to store these transient messages in their chat platform. If we want, we can use Amazon SQS or Windows Azure queue service for that purpose. Now one thing that we haven't talked about is push notification in this entire communication. So your interviewer can ask you to implement a push notification at this point or even before. But as you may know that this is just another feature and a lot depends on the implementation detail. So our main goal is to make the communication reliable once the message leaves the data center and makes it to the user's phone in least cost and also with maximum reliability possible. So that's something that we all need to keep in mind when we are designing this sort of push notification feature in any chat application. So this requires a little bit of networking or specifically TCP knowledge. But to still keep things as simple as we can implement push notification in 2 ways. Either we can do a client pull or we can do a server push. Then within client pull, there are 2 techniques that we can apply, which is like short polling and long polling. But if you want to do server push, we have 2 options. One is WebSockets and another one is server side events, short for SSEs. These days, WebSockets have become the de facto push notification system because it provides a full duplex communication channel to the server and client. Because as we all know, the nature of HTTP communication is just a single or half duplex communication channel. So once a request has been sent, the response has to be sent in another channel. So that's why clients won't have to open a new connection just to get the push notification, and same is true for in the case of server side events. But if you want to learn more about each of these communication protocols and how they are used in the chat application, we have explained this further on our website www.techtextula.com. So you can check that there. Link is always provided in the description. Also let us know in the comment section that if you want us to make a video on these different push notification techniques, we can also do that. But as we have some time left on our hands, so in a classic interview scenario, you would be asked to improve your design or tackle some of the scaling challenges here. So you can discuss some of the potential improvements or potential bottlenecks and optimizations here. So we have laid down some of these optimizations here. So first up is chat server failure. So it is very easy that the chat servers can go fail all the time. And one approach that comes to my mind is that once the chat server is going down, we just like literally take all of its connection and then open up into a new server. But that would be too costly. We can take a different approach, which is keeping our chat server pretty agnostic of their set of clients. And whenever a server goes down, we let the clients to start a fresh connection with a new server which is available and updates its location in chat storage server. This way we can make it pretty scalable and also cheap in terms of infrastructure cost. Next potential improvement could be that this transient storage can fail, as we have seen in terms of storing the media or images in these transient storage server, they can also go down. I'm pretty sure some of you already might be wondering that this might be a single point of failure and a good interviewer would definitely poke at it. What we can do about it? So we can definitely create a replica of these transient storage server and keep updating it. So when Bob comes online, we will simply call both the original instances and the replica and merge their data to send the undelivered message back to Bob. So as we can see here, we are spending a little bit more money to replicate the information between these two servers, but it is highly justified since we don't want to lose any messages because of bad server health. Another important point that the interviewers are highly interested is that how would you scale your platform? Like how many servers at the end of the day would you need when your traffic is spilling over? So for this, we need to get some rough numbers around the number of users, number of messages being sent or received, peak traffic, etc. etc. Let's say we have around 1 billion users, active users per month. And around peak, we can expect like 650,000 users to be using this service. We can also expect around 40 million messages being sent per second around this peak traffic. So here we will be talking about how to scale our chat service microservice layer, since that is the front facing service in our chat platform. So they are bottlenecked with how many concurrent connections they can open at any given point. So we have this formula that we can use to calculate the number of these servers in the fleet. So if we plug the numbers in this formula, we would have around 8 servers, which is not that high. But the important thing to pay attention is each server is opening up 100,000 concurrent connections, which is insanely high. So you can see that if you can manage to open up more connections on your servers, you would need a smaller fleet and so on and so forth. Fun fact for you guys, Rich Reed, lead software engineer at WhatsApp, gave a talk in which he explained how WhatsApp was able to support 1 million concurrent connections on each server using FreeBSD kernel and Erlang based server applications. Really nice talk, please go check that out. We have included that link in the description. But these are not the only optimizations we can make. There are tons more. For example, how to enable end-to-end encryption messages, how to show users last activity status, how to apply monitoring system to monitor the health of your services. These are only some of the topics that come to my mind. If you want a complete list, you can visit our website where we have covered these in a lot more details. With that, we would like to end this video. We had a lot of fun while creating this video and have plenty of other videos on our channel that cover system design problems in depth. You can check that out in our playlist here. And if you like this video, click the like button. Please also subscribe to our channel and hit that bell icon to stay updated about our future videos. Also leave us a comment if we missed anything in the video or you have any suggestions for any future videos. Also, as we have mentioned earlier, if you want an in-depth explanation of this video, please head over to our website www.techtakshila.com. Link is in the description. There you can play around with different brain exercises to fine-tune your knowledge about these topics. And as always, thanks for watching. Stay tuned. How to Design Netflix is coming up next.